Okay, good morning. So we have been discussing about ammonia enrichment process in the previous class, and specifically we discussed about deflegmator and the rectification column. Okay, so I told you that after the generator, whatever fluid is coming, that is our ammonia plus water, because ammonia vapor, though it has to be pure ammonia vapor, but along with ammonia vapor, there will be some water vapor also present. Okay, and then we are having this physical arrangement of having multiple plates, and through these multiple plates, actually, in the top we have used a cooling coil which will be condensing initially the water vapor and then ammonia vapor, so which will be dripping in downward direction because of the gravitational stratification, and whenever these will be passing over, interacting with the vapor medium, these will lead to cooling, multiple stages of cooling and separation, which we are utilizing for ammonia separation. Okay, so this is my rectifier column and this is the deflegmator. Typically, instead of using these vertical plates, we can also use some vertical tube, which is particularly for rectifier column, which is packed with some ceramic spherical balls. Okay, so instead of this, we can also have some arrangement, some packed arrangement of spherical balls. So in this case, what can happen? The vapor medium will pass through the interstitial spaces, and this will rise in the through the pores in the upward direction, and liquid will fall in the downward direction. Okay, so this type of instead of using this type of plates, this ceramic spherical balls can also be put inside the rectifier column. Okay, this can be some other configuration. Now, one important point we need to observe. You see, in this generator, from here, ammonia plus water vapor is actually leaving. But what is coming to the generator? Okay, usually in the generator, what comes? Can you tell me? Usually in the generator, strong solution of ammonia and water comes. That comes in the liquid form. Okay, so that strong solution enters from somewhere over here. But we know that the temperature of that strong solution is significantly less in comparison to the temperature of the generator. Is this one clear or not? So it means that this strong solution is also having some potential for transferring the heat to the vapor medium which is going out of the ammonia. Is this one clear? Out of the generator. Okay. So from this generator, whatever this ammonia and water vapor are going, this typically goes at Tg temperature, which is temperature of the generator, and the strong solution which is entering into the generator, it typically enters after the absorber, so its temperature should be close to absorber temperature if pump work is negligible. Okay, is this point clear? So it means this Ta temperature is very less in comparison to Tg temperature. So whatever the vapor is going up, if this strong solution also I pass through this type of plates, then ultimately what can happen, this vapor can even transfer heat to this strong solution coming from the absorber, and because of this heat exchange process, the load on the generator will also be reduced further. At the same point of time, enrichment of ammonia will also happen. Is this one clear? So now what we do in our deflegmator and rectifier, what we will be doing, we will be actually stopping up to some point. Okay, so instead of using the entire rectification in the rectifier column itself, we will stop somewhere over here, and this is the point where my temperature of liquid becomes close to absorber temperature. Okay, after this point, what I will do, I will take another column and I will integrate this column with generator. Okay, and inside this column also I will be having some vertical some plates like this. Okay, now you see what is happening. Exit of this is nothing but my state 3 to this. What is coming? Vapor. This is the vapor, and from here what I will be getting? Some liquid which is dripping in downward direction. So this is the dripping liquid, and along with the dripping liquid from side I will also add the strong solution which is coming from absorber. Okay, after the pump. So this strong solution, and from here I know that pure ammonia plus water vapor will be actually moving in upward direction. Okay, so this additional thing why we are doing, the purpose of only this additional thing is that we are reducing some load on the generator. Okay, and this will further helping in the ammonia enrichment process as well. So this bottom column which is integrated with the generator, this particular column is called as exhausting column, or it is also called as analyzer. Okay, so this column is typically known as exhausting column or analyzer. So now let's do the theoretical analysis of generator-cum-exhausting column. In integration, if we have this, then how this will behave. Okay, so what I have, this is the scenario. If I have to draw a control volume, this is my control volume. In this control volume, here I am having multiple plates. Okay, now tell me what happens from the bottom portion of the generator. What we get? We get saturated liquid from bottom portion. Here we get state 2. Okay, and typically this state 2 is nothing but, in saturated state we have mostly water plus small fraction of ammonia. Okay, because mostly it contains water. Is this one clear? It has to be a weak solution. And from this, what will be going up above? This will be vapor state. And from here, what will enter? We will be getting liquid state. So basically, two liquids are coming. One is the liquid which is dripping from the deflagmator. That one will come, and other the strong solution which is coming from analyzer, that will also join. Okay. So if this liquid state I need to define on actual cycle, then on actual cycle it will be, I think, 1 dash or 1 double dash, like after the pump. So if inlet to the pump is state 1, then exit to the pump, let me define as state 1 dash. Anyone is having any doubt about this? So these are all my mass interactions in this control volume. Other than that, I'll also be having one heat interaction. What is the heat interaction? This is generator-cum-exhausting column. Okay. So in this generator-cum-exhausting column, I am adding Qg amount of heat. Now we know already the analysis. First part, what we need to do? We need to apply mass balance. So what is happening? M dot L mass is entering, M dot V mass is going out, and M dot 2 is also going out. This is equation number 1. Anyone is having any doubt about this? What about second equation? m dot L into XL minus m dot V into m dot 2 into X2. Fine. Now m dot V I will replace. So if I replace m dot V over here, what I will be getting? M dot L into XL minus of, in place of m dot V I will be getting m dot L minus m dot 2 into XV equal to m dot 2 into X2. Okay, so from here m dot L into XL minus XV minus of m dot 2 into XV
minus X2.
X2 minus XV. No? Is it correct? Okay. Then if I calculate m dot L by m dot 2, what I will be getting? XV minus X2 divided by XV minus XL. So this is coming from concentration balance. M dot L by m dot 2 is clear to all. What next? Energy balance. M dot L into HL minus m dot V into HV minus m dot 2 into H2 and plus QG. QG is added to the system. Okay. So again I will be replacing m dot V. M dot V with what I will replace? M dot L minus m dot 2. Okay, so from here I will be getting m dot L into HV minus HL Is it correct? I have taken minus sign on the entire equation actually. Please tell me, is it correct or not? Whatever I have written. With minus sign, is it correct?
Yes.
Now let's do m dot L by m dot 2. Fine. M dot L by m dot 2 can be written as XV minus X2 divided by XV minus XL. So from here I will be getting HV minus HL divided by XV minus XL into XV minus X2 is equal to HV minus H2 plus QG by m dot 2. Okay. So what is this? This is coming from energy equation. And after doing substitution from the composition equation, so this is the equation of operating equation. Okay, this is defining the operation. Again, this is a straight line equation. So now let me plot these things on the enthalpy composition diagram. What I will be getting? Say at the condenser pressure, because generator will be working at condenser pressure only. Okay, at the condenser pressure I am having these liquid and vapor states. So again the concept is same. Liquid and vapor should not lie on the same isotherm. Okay, in order for the transfer of heat, vapor should have slightly higher temperature than the liquid temperature. Okay, so say somewhere over here is my vapor and here I am having liquid, where isotherm passing through this is this. So this is the isotherm. So it means vapor is on the left of the isotherm. It means the temperature of the vapor is more. All are clear with this point or not? Now what will happen? Tell me. What information I am having other than this? I am having information about state 2. State 2 will be state 2 will be a state of bit lesser composition. Okay. It has to be higher water content. Sorry, yes, higher water content, so less ammonia. Okay, so it means state 2 must be somewhere in the left side. Other than that, what I will be having, if I join this liquid and vapor, then this liquid and vapor will intersect with the composition of state 2. Okay, say this is my x2. When this line will intersect with the composition of state 2, that particular point is defined as P2. All are clear with this point? So what is P2? P2 is called second principal pole. Okay, this is called as the second principal pole. Okay, and this, the line joining liquid and vapor, this is the straight line whose equation is this. So this straight line will be nothing but my what? Operating line. This line will be operating line. Likewise, you see over here, this is the operating line. So in the similar way, this is my state 2 and this is the operating line. Okay, now if I have to draw a operating line, okay, let me first go over here. Let's consider slope of this is angle made by this line with horizontal is theta 2. Then what is the slope of this line? Tan theta 2, and mathematically slope can be written as HV minus HL divided by XV minus XL. Okay, so from here I can say that XV minus XL into tan theta 2 will be equal to HV minus HL. Is this point clear? Now if I use point 2 and point V, so if I write XV minus X2 tan theta, what it will be? HV minus H2? Correct? No, why plus Q2? You see, this point is, what is XV minus X2? This distance is XV minus X2. This is base. Actually this distance. So this is perpendicular. Okay. So what will be perpendicular? Simply base into theta, tan theta. So that is HV minus H2. Okay. Is it correct? Now, what is tan theta? Tan theta is again HV minus HL divided by XV minus XL, which is becoming identical to the left hand side of this equation, XV minus X2 into HV minus HL by this, correct? Okay, so what I can do, this I can replace with the right hand side. So what was right hand side in the previous equation? HV minus H2 plus QG by M dot 2. HV minus H2 plus QG by M dot 2 is equal to sorry, here I have written wrongly. I must write this XV minus X2, and this enthalpy will be becoming actually HP2. Correct? This is wrong. Please see this point again. You see 2 will be at saturated, so enthalpy will be corresponding to pole, that is P2. Is this point clear how this HP2 has come, or anyone is having any doubt? So it has become HV minus HP2. Now HV is cancelling. So from here I will be getting that HP2 equal to H2 plus QG by, sorry, H2 minus QG by M dot 2. Okay. Now you see H2 is a fixed quantity, QG is a fixed quantity, M dot 2 is a fixed quantity for steady state operation. It means HP2 will remain always a fixed quantity. Okay. So here you can see this part is HV minus H2. This particular part is H2 minus HP2. And what is H2 minus HP2? HV minus HP2 is basically QG by M dot 2. Okay. So this portion will become QG by M dot 2. All are clear with this point? So always again here also the slope of this line is steeper than the isotherm. Okay. Now how to draw the other operating lines? I can have one operating line. Every operating line must start from the same pole. So one operating line can be on the right side. One operating line can be on the left side. Now you tell me which one will be for right side, which one will be for left side. Like top plate or bottom plate. If I am at any arbitrary plate of the exhausting column, okay, if I move towards the bottom I am coming close to the generator. Close to the generator, temperature will be more. Okay, so if temperature is more, then in vapor side temperature increases towards the left side. So this blue color over here will be for bottom, and this will be, black one will be for top plates. Is this one clear? Any doubt about this? And when an operating line will directly pass through point 2, that will be our actually condition of saturation. Okay. All are clear with this point? So these are our multiple operating lines for multiple plates. So this is how our analyzer and actually analyzer and generator works. Is this point clear? So in total, in a practical system, what we will be having, because we have to do the ammonia enrichment, so we will be having combination of analyzer and generator and rectification column and the deflagmator. Is this point clear? Anyone is having any doubt about this? All are clear with this idea or not? Just please tell me yes or no. Okay, so now we will discuss the next type of system, which is lithium bromide and water vapor absorption refrigeration system. Okay, so let me tell you the aqua ammonia system. Yes, that will also join with this strong solution.
So we have to consider
that is. So ultimately what we do, because that dripping liquid amount is very less. Okay, majorly the composition will be dominated by the strong solution. So that's why if you see in the analysis I have simply taken the strong solution, but in the actual practical system that separately I have shown the dripping liquid also. Okay. So what we have now, vapor, so this aqua ammonia system, though aqua ammonia system is performance wise good, but the only issue was that presence of ammonia in the presence of water in the evaporator is actually problematic. Okay, so that's why in order to avoid that, we couldn't even completely eliminate that, but in order to mitigate that issue, we have to have this additional arrangement of analyzer cum generator and deflagmator cum rectifier. Okay, so this is a very complicated system. So if we have some combination where we are having the solutions whose say mixture is made up of, means the combination of refrigerant plus absorber. This is made up of some substances whose boiling temperature difference is say very high as greater than 200 Kelvin. Then you can actually achieve the 100% separation and you need not to go for this additional in the generator itself, and you need not to go for the additional arrangement of deflagmator, analyzer and exhausting column, etc. Okay, so these additional components are not needed. It means the system configuration will be simple. Okay, so though this is not exactly the reason for lithium bromide water system, but lithium bromide water system is having one other advantage. Lithium bromide typically is a salt. Okay, and it being it as a salt, it does not boil immediately. So as it does not boil immediately, here if I use water as my refrigerant, and lithium bromide is having strong affinity for absorbing the water vapor. So you see any salt, if you have, typically if we keep the our normal salt box open, what happens? After some time we see it is capturing moisture. Okay, so salts are typically having affinity to capture the water vapor. So if I use water as refrigerant, then at the exit of the evaporator I will be having actually water vapor. Okay, and if I use lithium bromide salt as my absorber, so what will be happening? This salt will immediately try to capture the water vapor. Is this point clear? So lithium bromide water system is having advantage that lithium bromide salt we are using, it does not easily boil in the generator. That's why we need not to use this complicated arrangement of deflegmator, analyzer or rectifier, etc. Simply generator will be serving the purpose and we will be able to achieve almost close to 100% separation of the refrigerant in the generator itself. Okay, so that's why lithium bromide and water systems are preferred, but there are certain limitations of these systems. First limitation is these systems, because water, if we are using water as refrigerant and if we go at temperature 0 or below 0, what will happen? Water will freeze. To avoid the freezing, evaporator temperature is typically maintained greater than 5 degree Celsius. Now, if we are operating some evaporator at greater than 5 degree Celsius, we cannot use this for applications where sub-zero temperatures are to be achieved. Okay, so this is typically used for air conditioning applications, because in air conditioning we typically need to maintain the human comfort conditions, which is 23 degrees Celsius temperature and 56% relative humidity. Okay, so 23 temperature is significantly larger than 5 degree, so my evaporator can be maintained for air conditioning at above 5 degree. Is this point clear? Second important point is, whenever we are using lithium bromide, along with the lithium bromide, always within the system there should be some water present. Okay, because if there is the presence of pure lithium bromide, then crystallization will happen actually. Okay, so again crystallization will freeze the pipelines and we will not be able to achieve the flow of the fluid. Okay, is this one here? So these are the advantages of lithium bromide and water system. Let me quickly draw the system also, because this will be a very simple arrangement. I will be having condenser. After condenser I will be having expansion valve. Then I will be having evaporator. Then I will be having absorber. Then pump, and here I will be having generator. Something will come from here, expansion valve, and whatever is going over here, this let me pass through a preheater. Okay, so here I will be having pure water vapor. Okay, here I will be having solution which will be strong in water and weak in lithium bromide, because more water composition is there. Is this one clear? So this has become, if you are now considering lithium bromide as the measure for defining composition, then this solution will be regarded as weak solution. Okay, so because if lithium bromide you are defining as your solute for defining the composition, then water is more, lithium bromide is less, so it will be becoming a weak solution. In the bottom, all the mostly the water will be evaporated, so here I will be having nothing but strong solution in lithium bromide, strong in LiBr. Okay, so this is the circuit. Is this one clear? So very simple cycle, you need not to use any additional arrangement, because in the aqua ammonia system, above generator you have to use exhausting column, then you have to use rectification column, then you have to use deflegmator. Otherwise that system is not practical. But in this system you need not to use all these arrangements. All are clear with this system? No. Here water is refrigerant, lithium bromide is absorbent. So vapor will become of water. Okay, water will be vapor. So please Read this carefully. Here water will be acting as refrigerant and lithium bromide will act as absorbent. Is this one clear? And typical applications of this system are in where air conditioning applications. Okay. Now let us talk about the final topic, that is the Platen-Munters system. Platen and Munter were two students who in 1920 demonstrated a system, and their system was having advantage that it's a pumpless system. There is even requirement, the requirement of pump is also not there in their system. Okay, and that system can be operated in the areas where there is no electricity, because for operating pump you need electricity. Okay, so it's a pumpless system. The only thing required is heat. Okay, so what's the block diagram of their system? So in somewhere in 1920s they have developed this system, and this system was in long use for domestic refrigeration, particularly in the regions where there was no electricity. Okay, so this system had many practical applications. So in the system we have actually multiple fluids. This system uses aqua ammonia only, ammonia as refrigerant and water as absorbent. But in addition to that, it uses one more additional fluid, which is hydrogen gas. Okay, so they have a condenser. From the condenser fluid, there is no expansion device. From the condenser, fluid enters into the evaporator. Then from evaporator it goes to absorber. From the absorber it goes to, in the generator there is bifurcation. Part is going to condenser and part is going to absorber. Okay, and in between the condenser and evaporator there is one more fluid which is over here involved. Very first point about this system, in this system the total pressure of all components is same. Is this one clear? So total pressure of all components is same. So it's a constant pressure system. You do not have any pressure difference in the evaporator and in the condenser. Everywhere pressure is same. So total pressure of the system is same. Why I am using total pressure word? Because we have multiple fluids. Okay. In the condenser, I will be having pure ammonia. Condenser, I will be having pure ammonia. From condenser, in the evaporator, sorry, this I have drawn wrong. It should be here. From the condenser, fluid has entered into evaporator. What has entered in evaporator? Ammonia. So from this side ammonia is coming, NH3. But from this side one more thing is coming from the absorber. What is this? This is hydrogen. Okay. From here what is coming? Hydrogen. So in the evaporator, now I have what? In evaporator I have ammonia plus hydrogen. Okay. So if my total pressure is same, then partly pressure is because of hydrogen, partly pressure is because of ammonia. So hydrogen is in the gaseous form and ammonia is majorly in the liquid form, but there will be small vapor. So here the partial pressure of ammonia will be very less. Okay, and if this partial pressure of ammonia is less than the vapor pressure of ammonia, then what will happen? In the evaporator, evaporation of ammonia will take place. You have to understand this with the help of simple example of air water system. You have a glass of water, okay, which is kept inside this room. In the surroundings you have air and water vapor. So in total atmospheric pressure, significant portion of the pressure comes from air pressure and small pressure comes from the partial pressure of water vapor. Is this one here? So atmospheric pressure is nothing but partial pressure of dry air plus partial pressure of water vapor. Whenever we say that our air is already saturated, what it means? In air, the maximum amount of moisture that it can hold, it is present. Corresponding to that situation, the pressure of water vapor will be maximum in the mixture. Okay, and once air is saturated, in this room if I have saturated air and I have put the glass of water, even if I come after 10 days and in all the 10 days my air is saturated, will I be having any level difference? There will not be any level difference. But if my air is not saturated, what it means? It means that the partial pressure of water vapor is less in comparison to the saturation limit. In that case, what will be happening? Some water vapor will keep on evaporating. Okay, till the pressure is reaching to the saturated condition. So I will be finding that my glass water level in the glass will keep on decreasing. Is this one clear? So same is the principle over here. Here what I am saying, that evaporator is having ammonia plus hydrogen. So it means the total pressure in the system is constant, but the pressure of partial pressure of ammonia is less in comparison to vapor pressure of ammonia. So what will happen in the evaporator? There will be evaporation. Okay, so another you have to understand one point. This process is purely evaporation process. It is not boiling process. What is the difference between pure evaporation and boiling? Please tell me. When I put glass of water, then what happens? If I keep on heating, then bubbles will come. Vapor bubbles will come in boiling process. But in evaporation process, if I have put the water vapor over here, sorry, glass of water over here, I will see that liquid level is going down, but there is no bubble formation. Mostly vapors are escaping from the surface. So in this case, because pure evaporation is happening, that's why in the evaporator there will not be vapor bubble formation. Okay, so vapor bubble will not form in the evaporator. Is this one clear? Now from the evaporator in downward direction, ammonia and hydrogen will go. In the absorber, ammonia will be absorbed by water. Okay, so here I will be having ammonia plus water. Then here ammonia will be going above and here I will be having water. So this is the circuit. Is this one clear? Now how this circuit can work without the use of pump? Let us understand this. So this was the schematic representation. Let me draw the actual system. Let us consider this is my condenser coil. And this is evaporator. What is this? Absorber. Generator. So this is the system. Okay. So here what I will be having? Ammonia plus water. This is my absorber section. In the absorber I will be having, in the bottom, what I will be having? Ammonia plus water. Okay. This is evaporator. In the evaporator I will be having mostly ammonia. Let me draw ammonia with blue colored thing. Here also I will be having ammonia in the condenser, and here all these will be ammonia vapor. Okay. And here I will be having water. Hydrogen let me draw with black colored circles. Now you tell me, is this circuit clear to you or not? Here I have to use some flame for heating this. So if I show over here with red colored dashes, I have represents water. I have represented water, and with blue colored dash I have represents ammonia in liquid state. With blue colored circles I have written ammonia in vapor state, and with the black colored circles I have represented hydrogen gas. Okay. And what I am saying is the pressure of this entire circuit is same. There is no pressure difference at all. Okay. Those who have class they can leave, those who don't have they can stay, and others can refer to. This is a small topic I will cover in next 5 to 7 minutes. Okay. Is this one clear? So entire pressure is same. Now you see, in condenser entirely what we have? Ammonia. In condenser what I have? I have pure ammonia. So it means the total pressure in the condenser is because of purely ammonia. If I go to evaporator, the total pressure in the evaporator, because I am using PT everywhere because pressure is same everywhere. Okay, so PT in the evaporator is equal to, because of ammonia plus because of hydrogen. Okay, pressure in the absorber, here total pressure is because of ammonia plus water plus hydrogen. You see here water ammonia mixture is also there and hydrogen bubble is also there. Correct? In the generator, total pressure is because of ammonia plus water. Partial pressure of ammonia plus partial pressure of water. Clear or not? Now you understand very clearly. One by one we will start. Let us first talk about generator. In the generator I am heating from the bottom. Once I am heating, what will happen? There will be formation of bubbles. Okay. And these bubbles will be mostly the pure ammonia bubbles because ammonia will evaporate first. When ammonia bubble will start rising in upward direction, in between two bubbles, some liquid will also be trapped. Okay, because whenever a bubble rises in a vertical tube, it is not only the bubble separately moving, it also, some liquid also get attached to it, or in between two bubbles also some part of liquid actually slides along with it. Okay, so because of the lower density, why these vapors are rising in upward direction? Because this is a gravitational system. These vapor bubbles have low density, so pressure everywhere is same. So if pressure everywhere is same and in between the vapor bubble is having low density, that vapor bubble will be rising in upward direction. Once it is rising, it will also carry certain amount of liquid along with it. So this is actually leading to the pumping operation. Pumping operation is happening in this vertical tube. Now we have a separator tank over here. In the separator tank, what will be happening? There is a big volume, so liquid will settle at the bottom and vapor from the top will keep on moving in upward direction. Okay, and this particular outlet is designed in such a way so that it always remains below the liquid level so that ammonia vapor cannot escape through this route. Is this one clear? So this outlet is to be selected in such a way so that it is always below the liquid level. Otherwise vapor can also enter in this route. Okay. So we have to avoid entry of vapor in this route. Correct? So it should always be below the liquid level. Now in this above vertical portion, what I will do? I will use some fins. So if I use fins, what will happen? It will transfer heat to surroundings. So if any liquid has entered in this portion, sorry, not liquid, if any water vapor has entered in this portion, that water vapor will be actually condensing and that will be dripping in the, because the here liquid amount will be very small. So if liquid is very small, that will be close to the walls. So it cannot now rise with the bubbles. So it will be settling in the downward direction and dripping down. So these vertical tubes with fins is nothing but acting as the rectification column or deflegmator. This is acting as deflegmator. Then here we have ammonia vapor now. So here also we will be having finned tubes. So all these finned tubes will be nothing but my now condenser fins. These condenser fins will give heat to the ambient and I will be getting over here liquid. You see here I am using circles and then here I have shown the long dashes. So it means vapor state in the condenser has converted into liquid. Is this point clear? Now this liquid has entered into the evaporator. Once this liquid entered into evaporator, from this tube hydrogen is also entering over here. Okay, so what this hydrogen will do? It will significantly decrease the partial pressure of ammonia. So if significantly the partial pressure of ammonia is decreasing, evaporation of ammonia will start in this process. If evaporation of ammonia is starting in this zone, then ultimately what will be happening? When something evaporates, it always creates cooling effect. Okay, it always creates cooling effect. So it means this portion of evaporator tube will be actually cooling. So if it is cooling, it means it is creating refrigeration. So this portion from here to here, it is acting as evaporator. All are clear with this point? Anyone is having any doubt? It is correct. Now what you have? Again a separation tank cum absorber. In this, of course, some hydrogen bubbles will also come and trap. Here again, here I have made a mistake. This point should be above the liquid level. This branch should be above the liquid level. Okay, so if this is above the liquid level, what can happen? Liquid from the bottom portion can enter over here, and this pipe should not be fully filled then, and vapor from the top portion, hydrogen vapor will be escaping and it will be rising in this direction. Correct? All are clear with this point? So this is how hydrogen will keep on recirculating within this portion. And from this separator, whatever the liquid solution was coming through the downward portion, that will be entering into the absorber. So this is how the cycle of absorber level will be maintained. And then this portion, so in the generator we already know, we have many times discussed in detail. Is this system clear? And in this system also, because in absorber we need to remove the heat. So typically what is done, this tube which is connecting the absorber to the, here fins are provided. So this entire portion is nothing but absorber. It is part of the absorber. Is this clear? So this system is something which works on the constant total pressure. Total pressure in all the components is constant. However, in condenser the total pressure is purely because of ammonia. In evaporator it is because of ammonia and hydrogen. In absorber it is because of all the entire three components, and in generator it is because of ammonia and water. And the mechanical configurations of the system we have chosen in such a way so that the pumping effect can be produced because of the gravitational stratification. Okay, so over here gravitational stratification is leading to the pumping effect. Is this point clear? Anyone is having any doubt about this? So this system is called as Platen-Munters system, because, and in general it's a pumpless system. Though its COP will be relatively less, being it as a pumpless, because naturally the flow is occurring. But again, it's very good system for the conditions where electricity is not present, and even it has in past, before the advancements towards electricity generation in many regions, this system was actually in use. Yes. Yes, yes, yes. Because it will be creating cooling effect. So once it is creating cooling effect, then it will be placed inside some refrigerated space, so that it will be cooling. Another important thing is, whenever this hydrogen is rising in upward direction, most of the hydrogen is, typically hydrogen concentration is more in the inlet of the evaporator. Okay, that's why the partial pressure of ammonia is very less in the inlet of the evaporator. So typically this portion of the evaporator is the more cooler portion in comparison to the remaining portions. Okay, so inlet portion of evaporator is the more cooler portion, because here evaporation rate is faster. Is this point clear? one very brief topic, that is properties of refrigerant and absorber. Let me quickly discuss and then this unit is over. Absorbent. So what should be the ideal properties of refrigerant and absorbent? In absorber, what we want? In absorber, we want that refrigerant vapor should immediately mix with the liquid. Okay, so the molecules must have attractive forces. Okay, so for having attractive forces, it means it should have negative deviation from the Raoult's law. When attract each other, volume decreases, which is a negative deviation from Raoult's law. In generator, what should happen? In generator, if the molecules have attractive forces, then these will not go easily. So molecules must have repulsive forces. Okay, so it means then in the generator it should show positive deviation from Raoult's law. Okay, because when molecules repel each other, then there is positive deviation from the Raoult's law. Yes, that's why the combination is difficult to achieve. But what is desired? We are writing here the ideal properties. Okay. Then third important point is boiling point of refrigerant should be significantly low than BP of absorbent. Typically the difference should be greater than 200 Kelvin. For ammonia water system, this difference is close to 138 Kelvin. At the typical operating pressure condition, of course it's a function of operating pressure, but typically at operating pressure it is 138. It should be greater than 200 Kelvin. That's why we have to use, because we couldn't achieve complete segregation in the generator, so we have to use deflagmator, rectifier, etc. for ammonia water system. Okay. Then fourth point is solution should be chemically stable at all temperatures. If it is chemically unstable, some chemical reaction can take place. These can form some other solution, and moreover, the chemical reactions causes irreversibilities. And even chemical reaction can lead to phenomena such as rusting, etc. Because rusting is also chemical reaction. So rusting, etc. should not happen. Fine. Number 5, freezing point should be low. If freezing point is high, then what will be happening? These may, in low temperature zones, it may freeze and it will be blocking the pipelines. Okay. So freezing point should be. Number 6, it passes through multiple pipes, so viscosity should be low, because if viscosity is more, then pumping power will be high. So these are some of the desired properties of the refrigerant and the absorbent mixture. Okay. So with this unit on vapor absorption system is over. From the next lecture we will start majorly our discussion, though we have a small unit on refrigerants also pending, but let me see if I discuss that unit at the end, then we will start our discussion on the air conditioning from the next lecture.